Here we have 8 charges of 1 nanocoulomb each located at the corners of this cube. The side of the cube is 1 meter. We are interested in the magnitude of the electric field at the center of the cube. One way to get the center point of the cube is to join opposite corners together. So we could join point O to point P and then get the midpoint of the line OP, which is about here. By symmetry, this center of the cube is equidistant from all 8 corners of the cube. The electric field at the center of the cube is the force on a charge of +1 coulombs. Let's consider the force on this charge due to the charge at T. Now the charge at T is a positive charge. It's 10 to the minus 9 coulombs. So this charge will feel a repulsive force in this direction. As a matter of fact, along the diagonal joining T to A. So if this charge is free to move, it would move towards A. Similarly, we have a force on this charge of +1 coulombs due to the positive charge at A, which is also 10 to the minus 9 coulombs. And because the distance of this point to A and T is the same, these two forces will have the same magnitude. Now if we sum these two forces, we'll get 0. So that's just for the charges at A and T. And of course, we'll have a similar situation for the charges at D and S. These two force vectors will add to 0. Actually, all 4 vectors here have the same magnitude. And finally, for B and R, we'll have this situation here. I'm trying to show this in 2 dimensions. And we must include B and R. We have P and O as well. The force on the positive charge due to P is directed towards O. And the force on the +1 charge due to charge at O is directed towards P. Anyway, all these vectors will cancel out to 0. So there are 8 force vectors acting on the test charge of +1 coulombs, and they sum to 0. Next, we will calculate the magnitude of the electric field vector at the center of any face. So let's take this face here. The magnitude of the electric field vector here will be the same as, say, the magnitude of the electric field at the center of this top face. Both vectors will point in different directions, but their magnitudes will be the same by symmetry, because the collection of charges are equidistant from either of these 2 points, and all 8 charges have the same value of +1 nanocoulombs. So let's work with this face here. Well, the force on this charge of +1 coulombs, which is the electric field at this point, due to, say, just these 4 charges here, will be 0 by symmetry. So we'll have 4 electric field or force vectors. Well, the electric field is nothing but the electrostatic force on a charge of +1 coulombs. So they'll cancel out for the corners PS, R and T. So we can forget about them. So now we're only interested in the charges at these corners. So let's consider the electric field due to the charge at A. Well, we draw a line from A to this point. I'll call this point C. And we just extend this line out, and there's our vector. It's pointing in a direction away from point A, because remember, we have a positive charge at A and a +1 charge here, so this charge will be repelled. So the electric field vector, which I can call EA, is in a direction out of the face. Now we can do the same for B. We can get the electric field vector due to the charge at B. Now what can we say about these 2 vectors? Well, they actually have the same magnitude. Why is that? It's because the distance of C to both points A and B is the same. This distance is the same as this distance. the electric field depends on the square of the distance. If the distance is the same, the field is the same, provided of course that these charges are the same. E also depends on the magnitude of these charges, and they're both charges of plus 1 nanocoulomb each. Now we have to do the same for D and O, so we connect D to C, and here is vector ED, the electric field due to the charge at D, and as for O, looks something like this. This is EO. Now let's see how we get vector ED. Well, we need the distance of D to the point C. We also need a charge at D. Well, we know that. It's 10 to the minus 9 coulombs. So we have the constant 1 over 4 pi epsilon 0 multiplied by the charge over the distance squared. Well, and that has to be multiplied by a unit vector that runs from points from D towards C, points from where the charge is, that is at D, towards the point that we're interested in getting the electric field at. So that's what we saw in the previous video. We saw that the directions will all work out correctly if we define our unit vector like that. So if Q is positive, then vector ED will be in the same direction as vector R. And indeed Q is positive here, so this will work out. So Q is plus 10 to the minus 9 coulombs. Now what about R? Well, if we can get the coordinates of this point, we can get the distance between this point and point 100. Well, C is midway between point T and point S. To get the midpoint of 2 points, we get the mean of the corresponding components. So let's look at the x values. That's 1 plus 0 is 1, and divide that by 2, so we get a half. Then we add the y values and divide by 2. 1 plus 1 is 2, divided by 2 is 1. And finally add the z values. 0 plus 1 is 1, divided by 2 is a half. Now, as we saw in a previous video, the unit vector R hat is nothing other than the magnitude of vector R, which we can actually write as just, well, I'm sorry, it's vector R, it's R with an underline, divided by the magnitude of R. I should have said the magnitude of R goes underneath. So this is the unit vector R hat. Okay, so we'll end up with R squared times R cubed in the denominator. And we vector R out here. So this is what we will calculate. So let's get vector R. So we're not interested so much in R hat now, but just vector R, which is easier to get. So how do we do that? Well, we just get the coordinates of the head of vector R and subtract the coordinates of its tail. So we take the coordinates of point C and subtract the coordinates of point D. So we have a half minus 1 is minus a half. 1 minus 0 is 1, and a half minus 0 is a half. So that's vector R. In other words, if we were to move the tail of vector R to the origin, then we'd look to something like this. The head of vector R would have coordinates minus a half, 1, plus a half. So that's what we mean by writing a vector as the coordinates of a point. Now in the notes you will see this written as a column vector. X value, Y value, and the Z value here. That's another way you can do it. So we could call this vector RD because its tail is at the point D. Now the R cubed in the formula is the distance of the charge to the point C. So we need the magnitude of this vector. So I just call that RD without the underline. So we're referring to D now in this, we're getting E here. So how do we get the magnitude of a vector? Well, we just square the components, sum them, and take the square root. So we have a half squared plus 1 squared plus a half squared. That's a quarter plus 1 plus a quarter. So we end up getting the square root of 1.5. So these units are assumed to be in meters. So this is what we get for RD. We want RD cubed, so we want to take 1.5 to the power of a half and cube it. Well, that's 1.5 to the power of 3 halves, and Q is 10 to the minus 9 coulombs, and we multiply that by vector RD. So basically we would be multiplying this scalar by each of these entries, each of these components, and that would give us the electric field vector ED, and then we could write it down in terms of I, J and K if we like. But that's just one vector, and you know, there are 4 vectors to consider. Well, one thing is that RD is the same for all 4 of them. RD is going to be 1.5, so RD will equal RB, if you want to call it that. That's the distance of B to C, and it will equal RA, the distance of A to C, and it equal RO, the distance of O to C. Well, the 4 vectors are different, but their magnitudes are the same, so we won't have to be worrying about calculating the magnitude. So we get the 4 vectors, and then we have to sum them. But when we're summing them, this quantity will be appearing in for each of the 4 vectors. So this scalar will be always there. So we can just take that out and just consider the sum of the 4 vectors. So I've only the sum of the 4 R vectors. So I've only RD shown here. So this is RD. But of course we need to get the others. So here's the shorthand notation for the sum. This is not a dot product, this is just multiplication of the charge by the position vector. So there we have the position vectors. So that Qi can come out because the Qi is the same for all 4 charges. And also this magnitude cubed can come out because that's the same. So that's what we have here, as we saw before. So basically we're just summing the 4 vectors. Now they're called R1, R2, R3 and R4 here. Anyway, let's go through the calculation of them. I won't call them R1, R2, R3 and R4. I'll call this one R0, the one from 0 to the point C. So we take the point of coordinates half, 1, a half, and subtract 0, 0, 0. Well, that's just going to give us a half, 1, a half. What about RB? Well, we take a half, 1, a half, and subtract 1, 0, 1. So we have a half minus 1 is minus a half. 1 minus 0 is 1, and we have a half minus 1 is minus a half. So there's vector RB. Again, we can write that as a column vector, a half, 1, minus a half. So that will just take the place of this column vector. We'll have the same quantity in front of it. And so on. What's left? Vector RA, I think, is left. So we take a half, subtract 0. Then we take 1, subtract 0. That gives 1. And finally we have a half minus 1 is minus a half. So a few of them are, well, actually only 2 of them are shown here. So the subtraction here is done using the column vector notation. It's exactly the same thing, just subtract the corresponding components. We'll have to sum the 4 vectors. So I've 3 of them written down here. So I'll just try to squash in RD again. We saw it already. And if we want to sum them, we just add the components. So you can see that if we add the x values, we get 0. Minus a half, plus a half, minus a half, plus a half will give us 0. If we add the y values, 1 plus 1 plus 1 plus 1 gives us 4. If we add the z values, a half plus a half, minus a half, minus a half gives us 0. So we will end up with vectors 0, 4, 0, or we can write it like this. So then, to get the electric field vector at the center of the face, we multiply each component in here by this quantity. Now if we multiply this by the x value, we'll get 0. So the x value of this vector is 0. Also the z value will be 0 when we multiply the scalar by 0. Now that's not too surprising. The x value is 0. So if we sum these vectors, they have no component in this direction. So by symmetry that kind of makes sense. Similarly, if we sum these vectors, you will see that they have no component. The sum of the vectors has no component in the z direction. But unsurprisingly, there is a component in the y direction. So the y component of all of these vectors, as you can see, is positive. The y component is in this direction. So when we sum them, we get something significant. So we get this scalar multiple times 4. Okay, so that's vector E. How do we get its magnitude? Well, that's easy. We just square the components, add them, take the square root. Well, the x and z components are 0, so they contribute nothing. We just square the y component. So we see we have to get the y component, we multiply this by 4. The 4's cancel out here, as you can see. We square it and then take the square root, but that doesn't do anything. So we end up with 1 over pi epsilon 0 by 10 to the minus 9 over 1.5 to the power of 3 halves. That comes to 19.57 newtons per coulomb, which is also actually volts per meter.